Okay. Cool. So I'm Felipe Menanteau. I'm from NCSA at the University of Illinois. And today I'm going to be telling you about what have we been doing using the Dark Energy Survey and the pipelines for the data management with the plan of trying to make a map of the observable universe. So for a while, we've been trying to make sense of it all. As astronomers, we've been trying to figure out our place in the universe. And I like this this drawing that is from the 1800s about, this is the astronomer trying to peek their head outside of the celestial sphere to see how everything fits, right? But as humans, for centuries, we've been trying to actually make maps, right? So we want to actually understand how everything is distributed. We wanted to understand the geography of our planet. And this is a map from Aristoteles from 200 BC. And that was the current understanding of the universe. And you can see parts of Europe, Libya, India, and other places, right? So we have come a long way since then. And the next efforts were in the 1700s, and most of you have heard about Charles Messier. So he was a French nobleman who was hunting for comets, right? That's what he really was after. And on the way of hunting by comets, he found a lot of stuff. And because he was the first one to do it, he called all of the objects M something, Messier, right? So M1, which you've seen it, is the Crab Nebula. There's M42, the Orion. And then we have on the kind of planetary nebula like M57 and M31. Of course, Charles Messier didn't have a happy ending. The French Revolution happened, and his work was cut short. But this is part of our effort as a civilization to map the heavens to understand our location. So I'm going to be showing you some pretty pictures and colors, and I want to make a disclaimer for the non-astronomers in the room, telling you that telescopes do not see in color, right? So, and this is actually how we make color images. So we observe in different wavelengths, we put filters, and then we assign colors to each one of those filters, usually RGB, and then we mix them. And that's how we create a color image. And of course, the color image are a fair representation of what they would look like if we have eyes of 3 meters and we could actually observe for 15 seconds or a minute of those. That's how they would look like. So as I mentioned, we've been in this quest for centuries to understand our place in the universe, and I think we made good headway in the last 100 years, right? So we should, we're part of that lucky generation that finally is trying to understand everything. And this is what we know about the universe, right? So we know that started about 13 and a half billion years ago with a big bang that immediately went through a very rapid expansion that we call inflation that can explain many of the phenomena that we observe, but it's only a theoretical framework. And in between, it's all that interesting stuff that we can see, right? So we have the CMB, and all in between, we have all of these structures, all of the astrophysics that's been happening in the last 13 billion years, all of the galaxies, the classes of galaxies, the stars, the planet, and the life, and us, right? And this is what we know right now. This is the current paradigm in cosmology, and it's a kind of complex paradigm, right? Because we know that we live in this universe that is very dark, and only 4% of everything is stuff that we have a clue, it's made of what we call baryonic matter, stuff like you and me, like the table, our planet, the hydrogen. The rest of the matter energy budget is completely made of stuff that we don't have a clue what it is, right? And in astronomy, we make up names for those, right? And we call it either dark energy or dark matter. So dark matter, which is another 20-something%, is some kind of particle that from cosmology, we try to pinpoint it using some experiments. From particle physics, there's other ways of doing it. But it's a particle that it's most likely not interactive, and it's cold. That's what we call it, cold dark matter. And the rest is, dark energy. And dark energy is a property of the universe that we don't know what it is, but it's actually making everything to expand, and not only expand, but expand at an acceleration rate. So most of the universe is actually invisible. So in order to be able to see anything, we need to create some kind of dark matter goggles or something that can probe all of the stuff that is basically invisible, right? So an example of how we're trying to do this is, without putting any labels, I think that most of you can figure out what that is, right? Right? That's Europe. So just like us, galaxies, houses, people are not uniformly distributed, right? So just like in most of the gangster films, you follow the money. In astronomy, what we try to do is like we follow the light. And that's the aim, right? So we can see galaxy. If we follow the lights, we can use the light as the tip of the icebergs and we can tackle two problems there. One is that regular matter, baryonic matter, the stuff that shines, the stuff that emits in the electromagnetic spectrum, is usually attached to dark matter, right? So they go together, they don't travel alone. And in addition, dark matter, together with the baryonic matter, they tend to sculpt, and with dark energy, dark energy tend to sculpt the distribution of matter. So by mapping the universe, we actually can put some constraints on these big unknowns that we have at the moment. So let me tell you about the project that we have that is called the Dark Energy Survey. And the Dark Energy Survey was started by trying to provide some answers to these big unknowns that we have right now about the nature of dark energy and the distribution of dark matter. And what it consists is a pretty big camera, what is called the Dark Energy Camera, DCAM. And in the previous slides, we have a photograph of DCAM, which is a 570 megapixel camera that is it's attached to a 4-meter telescope in Cerro Tololo in northern Chile. And the idea of this survey is that it's actually going to be trying to use 4 fundamental probes of cosmology to understand and try to figure this out. One of them is cluster counts, which is the growth of structure. The other one is weak lensing, which is making a map of the distribution of matter in the universe. The other one is large-scale structure, and the other one is supernova, that is measuring the expansion of the universe. So how are we doing this? We're doing this by mapping a large chunk of the southern sky. This is 5,000 square degrees, which is roughly a quarter of the southern sky, or a quarter of the southern sky, or maybe like an eighth of the whole visible sky. And we use DCAM, which is a 3 square degree field of view. And the survey, it started in 2013, it runs until 2018, and is roughly 100 nights per year. And that, of course, produces a lot of data. Of course, in astronomy, we measure everything in moon area units, right? Like everything else is in football fields in the US. In astronomy, we do it in moon. So I want to show the moon to give you an idea of how large the field of view is. Hopefully you can see it. And the DCAM is made of 62 CCDs that are basically 2K by 4K. It's of the order of 100, 120 iPhone 5s. And it fulfills its purpose, right? So it's big in order to cover, because what we want to do is map the southern sky. We want to find the galaxies and map them. We need to be able to do this fast and deep. By fast, we need to cover as much area as possible, and we also need to be very deep. Deep means that we need to find the faintest galaxies. Why do we care about finding the faintest galaxies? Is because by finding the faintest galaxies, we're actually looking back in time. So this is the scale of, so this is a foreground image that we end up having at the end in the slide, but what we're really mapping are all of those tiny galaxies that you see in the background. And this is roughly how it works, right? So this is the blanco at the center of the image, and you see those 2 clouds up there. Those are the large and small Magellanic clouds. And this is, if you were going to get out of the telescope, that's actually roughly the area that we're going to be covering. So it's a huge chunk. And this is what I've been doing over 5 years. And this is actually the observing. That was actually last November. And that's a typical night of observation. And you're going to see that the image, you're going to see how the Milky Way is moving around, and then eventually the sun rises. This is the footprint. That's the shape. It overlaps with Stripe 82 for the survey aficionados. They know what I'm talking about. It also overlaps with the SPT field, but it's mostly mapping a section of the southern sky that has never been observed before. And here we have a very nice animation made by Donna Cox groups at NCSA that shows the buildup of the survey over 3 years. And you can see each one of the hexagons that is popping up is one pointing. And we see how slowly, over a period of 3 years, we have been collecting data and building up both depth and the survey footprint. We want to do both, as I mentioned before, because we want to actually find the faintest galaxies. We want to actually go back in time. But also we need the coverage for the, to have a statistical sample. How are we doing this? So what are the problems? And I think there's assuming that, I think I'm going to have to skip because I don't think that it can be seen with this lighting. Oh, sorry. So what are the problems, right? So we get, and how Blue Waters is useful for this. So we get a lot of data, right? So we get roughly half a petabyte of data every night. And that's actually compressed. That doesn't include calibrations and all of the extra stuff that we get. And we need to get from this raw data into good images and actually catalogs from where we can extract the information about mapping these galaxies. And I would say that problem number one is actually doing this, is all of the image processing, which in our case is perfectly parallelized. And this is not the original design of Blue Waters, but it's something in which Blue Waters actually excelled. Blue Waters is basically an ocean of computers that we can send our jobs, and we are, at DESDEM, we're only limited by our own system that is actually sending the back and retrieving it. So we were able to, at the beginning, Blue Waters was not able to do this because most of our pipeline needs to communicate back to, to the mothership, and not all of the ports of communications were open. Now things work very well, and we'll be able to implement all our pipelines in Blue Waters. So as I say, the only, the reason why we cannot use more cores is not because of Blue Waters, it's actually because our own systems' inability to be able to send back and forth. So we're I/O limited by our own archive. So this is actually how it starts. This is just a section of DCAM, of the dark energy camera, and that's how the data looks like. It's full of instrumental signatures that we need to remove. We go and do what we call crosstalk correction. We do flat fields, and in the next step, you're going to see how we do the astrometric alignment. And you see how, which is, we align all of the stars on the galaxy to a reference frame because we need to have them perfectly aligned in astrometry in order to be able to co-add them and build up depth by observing these fields many times. So we do the astrometric alignment. We remove from bleed trails from the saturated stars. We remove cosmic rays. And then we start doing the second pipeline, which is the co-addition, which is once we have all of these inputs of all of the fields that we observe at individual epochs, we actually stack them to increase signal to noise. And this is how a co-added, the same section co-addeds look like, right? And of course, we also get rid of those gaps because we have an observing pattern that is going to observe over those. Right? And we're going to zoom in, and eventually you're going to see that we start seeing tons of galaxies, and this is what we end up having. This is the center of a very bright cluster at redshift of 0.3. And once we have this data, we can generate catalogs. And we have our own ways of running object detection, and we find and we map all of these objects. Once we map them, we can have the position in the sky, but we also have a position in terms of how far they are from us because we use photometric redshifts. So now we have a 3D map of the sky, and we can start addressing problem number 2, which is how do we go from catalogs to a distribution of matter? And in order to do that, we use gravitational lensing. So one of the effects of gravitational lensing is that it's going to shape statistically, it's going to change the shape statistically of the galaxies. Galaxies already come in very messy shapes. So this is a very complex problem that needs to be done very careful, but thankfully the community has been thinking about this for the last 2 decades, so now we have a good method. So how do we do this? So gravitational lensing, this is a real image, is the distortion by very massive objects of by the gravitational potential of very massive objects, in this case, a big cluster of galaxies, of foreground galaxies. So the light, as it passes through the gravitational potential, is actually bent and distorted. And this is actually what happens, right? So we have a galaxy in the background that is being distorted by the gravitational potential. So we, as observers, we don't observe the galaxies as they really are. They only observe them distorted. Their shapes have been shifted. So this is the kind of problem that we're trying to measure, right? So if galaxies were circle, we have no ellipticity, and then we can measure cosmic shear on the second circle, right? That's actually, like a 5% cosmic shear. But galaxies are ellipticals, right? So what we need to measure is a very, very small variation, and there's some alignment. So this is something that we've been able finally to do with blue waters, and we were able to finish running those about 2 weeks. And the result is that we end up getting something like this. We get like a distribution of the mass of the matter content in the universe at different redshifts. And we can use this to test against our models of galaxy formation and formation of the universe, because we know them, right? So we can, in a way, we can cook different universe, also using blue waters, for instance, and then we can end up with different realizations of it. And then we can confront those against the expectations. So when we do this for real, this is kind of like what we get. This is a matter distribution, I think at redshift of 0.4, coming from the science verification data. This is 1/10 of the survey area. Right now, we are in the process of actually creating these maps, and we've been able to do this using blue waters. So what are we be able to do? So we have all our production pipelines from DS Data Management, which it's a project that is centered on NCSA. We've been able to run those on blue waters. Which pipelines are those? The single epoch pipelines. These are the individual exposures that are coming from the telescopes. We've also been able to run what we call the multi-epoch pipeline, which is grabbing all of the individual exposures, combining them, and making deep catalogs. And then the weak lensing, which is extremely time-consuming, and we'd be able to run in a couple of weeks, something that would take months to run in any other cluster or ad hoc cluster. So, and this had been done with a fairly modest allocation of 120 kilonode hours. So let me summarize and end with a brief summary. So DES, the DS, the Dark Energy Survey DS produces a large data flow of 0.5 terabyte. We worked for about 2 years with the Blue Water team to run all of the frameworks on Blue Waters, and actually that was helpful. We open ports, we have real-time connections with the database, and all of our pipelines, even, we actually implemented all of our pipelines. We're not running all of them, but we are running all of those. We serve yearly data to the collaboration, and we also make public releases to the whole community. This is everyone, in astronomy or not. And we're gonna do 2 data releases. The first one is gonna be in December of this year, so it's coming along. We have very extensive outreach efforts with the Latino community in Urbana. We have also worked with documentaries, and we have one documentary about DS and LSST on Amazon Prime now. And we would like to believe that we've been a pathfinder to other larger astronomy surveys such as LIGO and LSST. So I'll stop here. Thank you.